repeat. Proving associativity is hard. I have to pick 3 arbitrary elements, apply the operator twice, essentially, in both sides, and show that I end up in the same place. And we've successfully done that for this operator. Move forward. Okay. For a binary operator star on S, we say that E is an identity element if operating with it gives me the original thing. A star E gives me A, as does E star A. So it has to work on both sides. For addition in all of our usual number systems, 0 is the additive identity, because adding 0 doesn't, on either side doesn't change anything. That's true for every integer, every fraction, every real number, and in fact, for every complex number. 1 is the identity element for multiplication, right? So the identity is associated with an operator, a binary operator. Different operator, different identity. Because 1 times anything gives me that thing back on both sides. For any integer, any fraction, any real number, any complex number. Except, the real important thing, yeah, I guess it's still true. Because 0 times 1 is 0, which is the same as 1 times 0. So, scratch that. In this order, that works. Okay, notice that for E to be an identity, it has to work on both sides. To state that in relation notation, I need 2 elements in the relation. I need AE to give me A, and I need AEA to give me A. So the identity element for 2 by 2 matrix multiplication is, of course, what?
1, 0, 0.
Yeah, the identity matrix, the 2 by 2 identity matrix. Right? And it's easy to show, and it's a worthwhile exercise, to show that if I do A, B, C, D times that, then I really do get A, B, C, D, by part of the definition of matrix multiplication, just as a reminder, on both sides. And if you do it by, the next way to do this, remember matrix multiplication, matrix times vector really means linear combination of the columns. So this one says, get the first answer as the first column. And this one says, get the second answer as the second column. Or dot product, either way. And it works on both sides. You can show that just by how matrices multiply, that this really does work. So you should convince yourself it does. Okay, we say that B is the inverse of A, denoted with a -1, even if we're in an additive group. So we keep it general. It's the inverse, B is the inverse, if A star B gives me the identity and B star A gives me the identity. So even in a non-commutative group, this has to work. Remember, matrix multiplication isn't commutative, but the identity matrix does commute with everybody. So in integers, right, 5/7 and 7/5 are multiplicative inverses, because either way I get 1. It's easy to show that this matrix is the inverse of that matrix. So if you do the product, including the 1/6 that's been factored out, I get 1. And you should remember how to do that from linear algebra. Okay. Next in-class problem. We want to find a complex number, which is the multiplicative inverse of 8 minus 6i. Remember, we're looking at complex numbers. I squared is -1, or we can say that I squared is the unique solution, is one of the 2 solutions to x squared plus 1 equals 0. I minus I will solve that equation. So what do we do? Well, let's brute force it, right? How about 8 minus 6i times a plus bi must be what? 1 plus 0i. Well, we can FOIL this thing. What do we get over here? We get 8a. If I multiply minus 6i times bi, what do I get? I get I times I, which is minus 1, so I get plus 6b. That's the real part of the answer. What must it be? If it's this, what must this part be? Must be 1, right? Because that's the real part of the other side. Now, what about the complex part of this answer? I have a minus 6i and a plus 8b, so I have minus 6a plus 8b must be what? 0, right? And how do we solve something like that? In your algebra, I row reduce 8, 6, 1 minus 6, 8, 0. Okay? That's the augmented matrix that corresponds to that equation. And what do I get? What do you get? This is a more pertinent question. Funny how linear algebra shows up in the strangest places. It's going to be a 2 by 3 matrix with 8, 6, 1, and 6, 8, 0. So I put in my matrix. And then second matrix, so I'm using this guy, right? I can do row reduction this way. Second matrix. And the magic button on this thing, math fraction. So there's the A and B. So if I multiply 8 minus 6i times 2 25ths plus 3 50ths I, you should do that and should prove to yourself you get 1, 0 as the answer. 1 plus 0i is the answer. Then you can do exactly the same thing. Row reduce, except having RSTU in here and do it by hand. You can get a formula for the general inverse of a complex number. Which, if I remember right, is the conjugate over the magnitude. Something like that. Let's move forward. Groups. We're now ready to define a group. We know what a relation is, we know what a set is, we know what a binary operator is, and we know what these terms mean, so that's all the stuff we need to define an algebraic group. It's a set with a binary operator that's associative, has identity, and everybody has an inverse. Okay, although it's implicit in the definition of a binary operator on a set, we have to be closed, right? When I say that star is a binary operator on S, I mean it's a map from S cross S to S, so by definition it's closed. But closure is also something we have to be concerned about if I'm starting with something that's not already stated to be a binary operator. So I have, if I operate two things in S, the answer has to actually be in S. And notice we don't demand commutativity for a group. Remember that not every group is commutative. If AB is equal to BA, again, for every pair, only for every pair commutes, we say it's an abelian group after Niels Heinrich Abel, the guy who actually proved you can't solve the quintlet and made some strides in abstract algebra. Okay, as stated before, Z is a group. The integers are a group with addition. Q with 0 taken away is a group under multiplication. In fact, those are both abelian groups. And the set of invertible 2x2 matrices with matrix multiplication is a group, but it's not commutative. So the general linear group is a non-commutative, non-abelian group. Okay, examples and non-examples. Z with plus is a group. The identity is 0. Integer addition is associative by assumption. Negative A is the inverse of A, because if I add those two, I get 0. Integers with times has identity 1. Integer multiplication is associative. There's an extra parentheses there. It'll be quicker. But only 1 and minus 1 have inverses. For example, to prove that this is not a set where everybody has an inverse, I need one counterexample. 2x equals 1 has no solution in this group because the only solution is x equals 1/2, and that's not an integer. So integers of multiplication are not a group. Now recall from linear algebra, the set of all matrices n by m, well, that's what the symbol is. The 2x2 matrices of multiplication has identity, is associative, matrix multiplication is associative, but not every matrix is invertible. Remember, to get the inverse of 2x2 matrix, I take the determinant, 1 over the determinant, I swap the diagonal elements and change the sign on the off diagonal elements. But that only works if AD minus BC is not 0. That's the determinant of that matrix. So there are non-invertible matrices like this one, whose determinant is 18 minus 18, which is 0. So the set of all 2x2 matrices with multiplication isn't a group. If I make it addition, it is the set of all 2x2 matrices. In fact, this set of any fixed dimension with plus is a group, because it's closed, the 0 matrix acts as the identity, etc., etc. But with multiplication, we have to restrict to invertible matrices. So that's how I get the general linear group, by restricting myself to invertible matrices. And fortunately, the product of invertible matrices is invertible, which keeps my closure. Okay. Do we have time? Yeah, let's just get these two theorems and we'll call it a day. Okay, the identity in a group is unique. We did this proof in class. How do we get it? Really simple. Assume that I have 2. Then this chain follows directly. E2 must be the same as E1 times E2 because E1 is the identity. But this must be E1 because E2 is an identity. I've shown that E2 and E1 are the same thing, proving that there can only be one, essentially by contradiction. Assume there's 2 and ending up showing they must be equal. And a very similar idea works with inverses. suppose that B and C are both inverses of A. Then BA must be the identity, and AC must be the identity. So B is B times the identity, but I can write the identity as AC. I'm in a group, I have associativity, that's one of the things I demand, so I can put into parentheses, but BA is the identity. And so I just proved that B and C must be the same thing. This is a very common way of proving things. If I want to show that B and C are the same thing, I start out with B and turn it into A. And notice I made the substitution at just the right point. Here, I turn E into AC because if they're inverses, that's true. And here I turn BA into the identity because I have that equality, my substitution. Okay, notice we use the facts about the problem along with the associativity of the group operator to establish the chains. These two theorems illustrate the power of the abstract approach. We prove a thing once in this general setting where we haven't said anything about that binary operator except that it behaves the group properties. It's often easier here. For example, once we show that the set of invertible matrices, and by n invertible matrices, is a group, we know there's only one inverse. We don't have to look for another. So for any group, once I know it's a group, I know its identity is unique, and I know that matrices and inverses are unique. And that's a good place to stop. Friday we'll pick up with this. We have a long way to go.